Welcome to my talk for the Bernoulli IMS One World Symposium 2020. I would like to thank the organizers for giving me the opportunity to present some of my recent research here. Today I will talk about the inhomogeneous circular law for correlated matrices, which is joint work with Torben Krüger from the University of Copenhagen. I want to start with something you're all familiar with, namely the circular law. The setup is as follows. X is an n by n random matrix with independent entries, such that all entries are centered and of variance 1 over n. In this case, X will not be Hermitian and also even not be normal. Moreover, most of its eigenvalues will be complex. We'll denote all eigenvalues of X by zeta 1 up to zeta n. And with this notation, the circular law reads as follows. If I evaluate the test function f at all eigenvalues zeta 1 up to zeta n and take the average of these function values, then this converges as n goes to infinity to f integrated against the uniform probability measure on the unit disk in the complex plane. This convergence holds almost surely and for all bounded and continuous functions f. This phenomenon is visualized here on the right in an example. The circular law has a long history, as you can see from these many references listed here. For today's talk, my goal will be to present an analog of this circular law to you if the matrix X has correlated entries. Here we will allow for very general types of correlations. Without any specific structure, we will just impose a certain decay condition. To make this more precise, I want to explain to you the precise setup and assumptions that we will use in the following throughout the talk. X is a random matrix whose entries are labeled by the index set omega. This index set is equipped with a metric D, and the index set has size n. Furthermore, we assume that the entries of X are all centered and have finite moments in the following sense here. In particular, the variance of the entries of X is of order 1 over n. This ensures that the eigenvalues will stay of order 1. For the metric D, we assume the following finite volume growth condition. The size of any ball in the metric D is supposed to grow at most polynomially with the radius r. Then the crucial assumption on our random matrix is the following decay condition on the correlations. For any two test functions f1 and f2, we assume that the covariance of f1 when evaluated at the random matrix X and f2 evaluated at X decays faster than any polynomial and any inverse polynomial power of the distance between the support of f1 and the support of f2 in the product space omega times omega. For the variances, we assume the following lower bound, which is expressed in a quadratic form sense. This ensures that our model has a lot of randomness. Finally, we assume that the conditional probability of an entry X, when conditioned on all other entries of the matrix X, has a bounded density. For the experts among you will know that to prove a convergence result for the eigenvalue density of a non-Hermitian or non-normal matrix, you need to control the smallest singular value. This condition E here, we use it exclusively to get sufficient control on the smallest singular value in our setup to prove our main result. Our first main result is the inhomogeneous circular law that I obtained recently in joint work with Torben Krüger. It reads as follows. We assume that X satisfies the conditions A up to E that I presented to you on the previous slide. Then there exists a deterministic probability density sigma on the complex plane, such that if I evaluate a function f in all eigenvalues zeta 1 up to zeta n of X and average these function values, then this is well approximated by f integrated against the probability density sigma as n goes to infinity. This convergence holds in probability and for every bounded and continuous function f on the complex plane. Such a result is called a global law because the test function f will see a macroscopic number or macroscopic proportion of the eigenvalues of X. And later in the talk, I will also show to you a local version of this statement. For random matrices with independent entries and a variance profile, global laws have been obtained before, and here are some references. To define sigma, I will introduce now the operators S and S star. Both of them map n by n matrices to n by n matrices in the following way. The matrix X is mapped by S to expectation X A X star, and S star of A is equal to the expectation of X star AX. These two operators capture all covariances between entries of X, and they will completely determine sigma. In the following, the square root of the spectral radius of S will be of crucial importance, and we denote this square root of the spectral radius by capital R. Then for any tau in 0 to R, there exist unique positive definite matrices V1 and V2, both are n times n matrices, such that the two coupled n by n equations, n by n matrix equations here are satisfied under the constraints that the traces of the two matrices coincide. Given V1 and V2, we can define sigma of any z in the complex plane by this formula here. And from this formula, we obtained the following properties. First of all, it's obvious that sigma is radially symmetric. With considerably more work, one can also prove that sigma has upper and lower bounds on the open disk of radius r in the complex plane. And due to this characteristic function here, we know that the support of sigma is included in the closure of the disk of radius r in the complex plane. And due to this lower bound here, we know that the support must agree with this closed disk. In particular, these two parts together imply that sigma will have a jump discontinuity at the edge of the support, so at the edge of this disk. And inside the disk, sigma is a real analytic function of the modulus squared. So we completely understand the support and regularity properties of sigma. Now I want to illustrate this to you in an example. So for a random matrix X with centered and independent entries, the operators S and S star are completely determined by the variances of X, of the entries of X. In this example here, we consider the following case. In the first half of the entries have variance 1, and the second half has variance 1 over 10. Then we rescale the matrix in such a way that the spectral radius of S's of order is equal to 1. Then we get the following histogram for one realization of X. And in red, you see the sigma that I defined to you on the previous slide. So you see I took a large n, I guess 2000 or 4000 or something like this. And in that case, we see a very good agreement between the sigma, the deterministic sigma and the histograms. As I told you before, we also have a local version of the inhomogeneous circular law. So that's the local inhomogeneous circular law. For X, we assume the same conditions as A up to E as before. And now we look at local observables. This will replace, so the local observables are called FWA. They will replace the F that we had before. They arise as follows. We take a function, we start from a function F, we center it around W and zoom in such that that the support will have a diameter n to the minus A. And we rescale it finally in such a way that the L1 norm is preserved. These local observables will then see a mesoscopic number of eigenvalues if the A is chosen sufficiently small. The theorem that I proved together with Torben Krüger is the following. We assume that the shift W is in the bulk spectrum of X. So that means we have to stay away from the edge of the disk with the radius square root of the spectral radius of S. That's imposed by this condition here. And we take an A between 0 and 1/2. And then we look at the same observable as before, except that we replace the F by the FWA, and also on the right-hand side here. So that means again that this quantity becomes deterministic when n is very large. We have an essentially optimal error term, rate of convergence here, and this convergence holds with very high probability for any sufficiently regular F. Let me stress to you that the upper bound 1/2 is in fact optimal, so we can prove this local law on the optimal scale, because if A is 1/2, then this observable will depend on the fluctuations of individual eigenvalues, so we cannot expect that this quantity becomes deterministic for large n. For random matrices with independent entries, such local laws have been obtained before. Here are some references. And the local law has an interesting consequence, which is the isotropic eigenvector delocalization. If I start from a bulk eigenvector u, then this corollary states that if I compute the overlap of u and v, where v is a deterministic vector, then this overlap is actually very small for any vector. And that says that there are no exceptionally large directions, or there are no directions where u is exceptionally large. In particular, if you compute this for a basis, it means that the u is essentially flat, because for a basis, for a deterministic basis, you would expect that all these overlaps are at least of size n to the minus 1/2. So then I want to conclude and summarize the things I've presented to you in this talk. I've showed to you an analog of the circular law and its local version if the random matrix has correlated entries. Here we can allow for very general types and classes of correlations. They do not need to have any specific structure. We just need these correlations to decay with respect to some metric. In general, the limiting density sigma will differ from the circular law. However, we have a very good understanding of the support and regularity properties of sigma. All results I presented to you today, you can find them in this recent preprint. And I finally would like to thank you for watching my video, and I'm looking forward to your questions in the discussion session.